Today we're going to talk about estimations, graphs, and mathematical models. But first we want to talk about place value so that when we talk about rounding, it will make more sense and you will round to the proper locations. So here I've got a number. We've got 210,987,654,321 and 23,456 hundred thousandths. Now, what a weird way to say that word. A couple of things that we definitely want to notice here, and those would include things like where this decimal point is. That's going to be key. All of the values to the left of that decimal point are 1 or greater. The values to the right of the decimal point are less than 1. And so we will take advantage of that. Now, they do have these commas in here. In the United States, we use those to differentiate between the hundreds, thousands, millions, and billions. In other countries, I noticed that they swap the decimal and the comma such that they use a decimal to separate hundreds, thousands, millions, and they use a comma to separate whole numbers from partials. And that can get a little confusing, but you get used to it if you're there. I got to spend some time in South America and a little bit more time in Europe. And so I got to see that and I got used to it. So I'm sure you would too. So let's talk about rounding for a minute. We will just look at maybe this portion of our number. So we have 654,321. That would be our number. And if we wanted to round to the nearest thousand, we will follow a procedure such that we will find the thousands place. That's right here. Now that we've got ones, tens, hundreds, thousands. So this is the spot we're looking at right now. And what we need to do is we need to look to the number just to the right of that. Just to the right of that is this 3. If the number to the right is 5 or larger, we increase the number in our desired spot by 1 and change the rest to zeros. When I say the rest, I mean to the right. So that's if the number is 5 or larger. Now, ours is not. If less than 5, just change it and all the numbers to the right to 0. Okay, so ours is less than 5. So we would just change it and everything to the right to 0. So this number, 654,321, rounded to the thousands place, is 654,000. Done. So let's now round to the 100,000th place. So we'll take our number 654,321, and we will find the 100,000th place. That's right here. So that would be our 6. Remember, we've got ones, tens, hundreds, thousands, 10,000s, 100,000s. So we look at the number just to the right of that. If that number is 5 or larger, which it is, then we increase the number in the position we want to keep by 1, change the number to the right to a 0, and all the others to a 0. So 654,321 rounded to the nearest 100,000 place is 700,000. So that's the difference between rounding. Now, you may go on to a more scientific realm, and in the sciences, we round it slightly differently, but very slightly differently. So go ahead and stick with this rule, especially for Math 123, and you'll be just fine. So that is our rounding. And again, those are for numbers greater than 1. But let's look at these numbers over here. Well, specifically those to the right of the decimal. Now let's look at their names. Notice we don't have a ones place. We have a ones place, but not a once place. We start with tenths, but I also want you to notice that all of these numbers to the right and in THS, that right there tells me that this is to the right of the decimal. So it's a part of a whole. It's not a multiple of a whole. Notice all of the endings to all the words over here to the left don't have, as a matter of fact, they've just got S's at the ends. They don't have the THS. So if it has a THS, it's to the right of the decimal. And again, there's no once place. And I like to think about it in terms of money. So if I have $3.42, what do I have now? These are dollars. So how much of a dollar? These are the dimes. So those are tenths because there are 10 dimes in a dollar. So this is the tenths place. These are the pennies. How many pennies in a dollar? There are 100 pennies in a dollar. So these are the hundredths place. So we don't have a one-th of a dollar. Those are dollars. So don't think about one-ths place. Think about tenths, hundredths, thousandths, and so on. And so let's go ahead and round this number 1.23456. We will round it to the hundredths place. Hundredths, we've got tenths, we've got hundredths. That's this place. Again, I look to the number to the right. If that's 5 or larger, then I bump this up. Because it isn't, I'm going to just leave the 3 where it is. 3 is in the hundredths place. It's the only one that might get bumped up to a 4. It would get bumped up to a 4 if the number to the right was 5 or larger. It is not. So it stays as a 3. Now let's do this again, but now we will go. Oh, that was thousands. Here I'm talking hundredths, and I tried to. Oh, that was right. Man, I need to take a nap. All right, hundredths was right there. Now let's go to the thousandths place. We've got tenths, hundredths, thousandths. I look at the number to the right. It is larger than 5, so I need to add 1 to what we're looking at, and that'll be 1.235. That's how that number will round to the thousandths place. So regardless of whether we're above 1, meaning to the left of the decimal, or below 1, to the right of the decimal, you're going to pick the spot you're looking at, and that will be based on the name that they told us to round to: hundredths, thousandths, the 10,000s, or the 1 millions place. Look at the number to the right. If the number to the right is 5 or larger, then the number in the position we're interested in gets bumped up by 1. And everything to the right of that either becomes 0 if it's to the left of the decimal, or gets dropped off if it's to the right of the decimal. If the number to the right is less than 1, we leave the number in the position we're interested in as is. And if we're to the left of the decimal, we change everything between that position and the decimal to zeros. If we're to the right of the 0, we just drop it. Now we drop it because adding zeros just says that we can measure to a greater precision. And so it's really a matter of precision that we're talking about at that point. When we're talking rounding in this class, just go ahead and follow that procedure. Just drop those zeros if they're there. Another number you may be familiar with looks a lot like this: 3.14159,265. That's about equal to pi. Pi is a ratio of a circle's diameter, well, the circumference to the diameter. So the distance around the circle divided by how far across the circle is. That's pi. So if we wanted to round this to the thousandths place, it's got the THS, so that's to the right. We've got tenths, hundredths, thousandths. That's the one we're interested in. Look to the right. It is larger than 5. Oh, it's 5. So we're going to add 1 to the number in the position we are talking about, the thousandth place, and we'll drop the rest. So this has now been rounded to the thousandths. Normally we round it to the hundredths. We usually use 3.14 if we're not going to use the full value of pi. Our calculators often have the full value of pi in them, but if you don't want to use that, you can round to 3.14 in this class. Now, why would I care about this? Why do I want to round? And the answer is because it makes your life easier. It just does. Let's pretend we're doing a little shopping. We're going to buy some bread. We're going to buy some detergent. We're going to buy a sandwich because it's just about lunchtime and we're hungry. We're going to buy an apple because keep the doctor away and all that. And a little something to wash it down. Except this coffee, we're going to buy like a tin. So let's say the bread costs $2.59. The detergent costs $5.17. Sandwich costs $3.65. The apple costs 47 cents. And the coffee we'll say is $8.79. You take that to the register, they ring it all up, and they say, you know what, that's going to be $24.67. So you pull out your card and you pay for it. Were you gypped? Did they charge you too much? Sometimes the computers are off and you get charged too much. If you know how to round and you're paying attention, you would know if this was too much or not. So let's go ahead and round these and let's see what the value prob would be near and see if that was too much or too little. So maybe I round these to the nearest dollar. Well, the bread, that's like $3 because the number to the right is 5. The detergent would be 5. The number to the right is 1. Number to the right of the 3 is bigger than 5, so we'll round that up. The number to the right of the 0 is less than 5, so we'll round, just drop it. Number to the right of the 8 is larger, so we'll add that up. Now we add these together. 5 and 4 is 9, and 9 is 18, and 3 is 21. So it should have been closer to $21. Now, every semester I have students say, well, what about the taxes? And that's a fair question. Our tax rate in Idaho is 6%. So 6 cents on every dollar. 6 times 21 is $1.26. So if I add that to the 21, it would have been 22.26, certainly not 24.67. So there was a mistake in the computer. And they charged me too much for one of these items. And I know that because I took the time to round. Maybe we round to the nearest dime. So this would be like 260 because I'm worried maybe I rounded that 47 down. Maybe that's the problem. This 5 becomes 520. 365 becomes 370. 47 cents becomes 50 cents. And 879 becomes 880. And we can add those together. Of course, there are zeros here. 2 and 8 are 10. And 5 is 15. And 7 is 22. And 6 is 28. 8 and 2 are 10. And 2 is 12. And 5 is 17. And 3 is 20. So $20.80 if I rounded to the nearest dime. It's certainly not 24.67, even with sales tax added in. So again, there's a problem with the computer. Now, if you're not interested in making sure that you're watching your money, you could just pay that 24.67 and walk out and you wouldn't know the difference. The store would make a little extra money and you would be out an extra, what, $3? If $3 doesn't mean that much to you, no big deal. You've helped the store. So maybe you're interested in doing that. And if that's your thing, go ahead and pay the 24.67. But perhaps it's better just to make sure that you're paying attention to those things so that when it does matter, you won't be taken advantage of. Another type of problem we might see, let's say a carpenter works full-time and makes $28 an hour. We're asked to estimate their weekly and annual salary. So weekly, full-time is 40 hours times $28 per hour. Now, why did I multiply these? Notice I write this per hour as divide by hour. So I have hours in the numerator in the top and hours in the denominator at the bottom. Notice those kind of cancel each other out, and I'm left with just dollars. Well, 40 times 28 is, let's see, let's try to do something so we can do this in our head. Maybe we round one of these to a number that is close, but easier to do in my head. Maybe I round this to $30 an hour. Because I can do 4 times 3 in my head, that's a 12. And then there's a 0 from the 30 and a 0 from the 40. So it's $1,200 per week. Now, what if I'm worried about that rounding? I can bring up a calculator and I can do 40 times the 28 and see what it actually is. It's 1120. So it was actually about equal to 1200. It is equal to, I forgot the number, 1120. So by rounding up one of those numbers, our value is a little high. But that's okay. We can deal with that. One of the things that might offset this is our annual. So 40 hours per week times, now I should do per like the same way, right? Times $28 per hour. Now this is annual, and we have 52 weeks per year. So let's see what cancels here. I've got hours on top, hours on the bottom, weeks on the bottom, weeks on top. I'm left with dollars per year. So that's pretty slick. Now, again, a little hard to do in my head. Maybe I round this up to a 3 and this one down to 50. No, let's go ahead and put that on up here. Now I've rounded one up and one down. Maybe that'll work well. 4 times 3 is 12, and 12 times 5 is 60. And then I have a 0 from the 40, a 0 from the 30, and a 0 from the 50. So about 60,000. Oh, let's see what we actually get if we plug it into our calculator. Remember, in the homework, you'll be asked to estimate, which means they'll want you to round. So we get 58,240 if we actually multiply those three together. Now, maybe 2 of those weeks are vacation weeks, and it is actually 50. Regardless, we're pretty close. Isn't it interesting? We rounded the hourly up by 2 and rounded the weekly down by 2, but it still was off. And that's because of how many times 28 shows up and how many times 52 shows up. 28 per hour, we have a whole bunch of hours in there. 52 weeks, well, that's once per year that happens. So that's what throws things off a little bit, but we have estimated it. Now, I was always told to estimate your yearly, you take that hourly wage, double it, and add 3 zeros. 28 times 2 is 56. Add 3 zeros, so 56,000 is about what you would make. That assumes that you get 2 weeks off for vacation. You've got some holidays in there and so on. But it's interesting how it works sometimes when we're estimating. So estimating, you're going to do some rounding. And you're going to round numbers that make it easier for you to do the math in your head. That's really what you're going to be looking at when you're doing rounding. There are some problems they give us that they round in a way slightly different from us, but they have also done us the favor in that the answers they accept are within a range of values. And when they do that, then it means as long as you're close, you'll be okay. On exams, you will be taking exams on the computer, but I will be able to go in and look at your scratch paper and award partial credit if you had it rounded differently from what they expected. So we'll take care of it. But do your best to round in such a way that it makes it easier for you to do the math in your head. What we have here is a pie chart. Now, with a pie chart, you are looking at percentages of the whole. And all of those percentages have to add up to 100. Otherwise, it's a misuse of a pie chart. But what they did with this particular one was they asked a bunch of people. Let's see, I think they asked them, well, it indicates how Americans disagree as to when old age begins. The question is, what is your definition of old age? And I can't remember how many people they asked, but they will then say, well, 41 of them said it was a decline in physical ability. 32% of those who responded said it was a decline in mental functioning. Others said it's reaching a specific age, or it's retiring, or becoming a grandparent. All of those things. I think that becoming a grandparent is funny because of how many teen pregnancies there are. If a teen at 15 gets pregnant and then her child gets pregnant at 15, well, at 30, she becomes a grandparent, and that's hardly old age. But that's the way it works. So let's see what we have here. Now, I want to also share with you that a lot of these problems can be solved using an equation like this: A equals P times B, where what we mean is A is often means equals. P%, so some percentage of in English, when converted to math, means times. And then we just have B. So A is some percentage of B. And we will write it out that way. Now, interesting thing when we use percentage in math problems, like if I look at this 41% that occurs in dark blue there, if I want to use that in math, I need to convert it to a decimal. Now that word percent, we could write it with a space where we have per cent. And per means divide, and a cent is a hundredth of a penny. So if I take that 41% and I divide by 100, I get 0.41. So that's the decimal equivalent of 41%, is 0.41. You just move that decimal. Now, I know you don't see one there, but if you don't see one, it's understood to be to the right there. But you can move it 2 places to the left to get the decimal equivalent of that percentage. We can always do that. So 32% equals 0.32. Just moving that decimal 2 places to the left. And when we get to the financial portion, we are going to do that a lot. So you'll get really comfortable with that by chapter 8. But for now, that's the calculation we'll use. So we've got this, and let's say we've got 249 million 19,818 individuals who are 25 years or older. And we will determine how many of those define old age by a decline in physical ability. So the decline in physical ability is here, and the corresponding percentage is 41%. So 41% of that number, 41% is 0.41 of is times the 249,019,818. That's not one I can do in my head, but maybe I just round this to 0.4 times, oh, let's say 250 million. That one I can do in my head, because 4 times 25 is 100. And then we got to take care of these zeros here. Now, half would be like 120 25 million. We're at 100. So 40% is a little less than that. So 100 million is what we would get there. Interesting, huh? Well, let's go ahead and plug this bigger one into our calculator. 0.41 times 249,019,818 and see what we get. 102,098,125. 102,098. 125, I think it was. So we're really close by rounding, and it was something we could do in our heads. So that rounding can really help just a bunch. One of the types of problems we might get would have a bar chart. So let me show you what a bar chart looks like, so you will know how to deal with that. When the screen goes kind of dark like that, I'm actually copying on a second screen. So here we've got a bar chart showing the life expectancy in the United States based on the year we were born. So those of us born in 1970, well, we've got two different colors there. Now, what do those represent? If we look up here at the legend, we see that the red is males and the yellow is females. So based on this, I can expect to live to the age of 67.1. So I've got 14 more years. A little bit later, you would expect to live a little bit longer. Now, notice in every case, the women are expected to live longer than the men, and that's just fine. Sometimes that's the way it works. In every case, from decade to decade, the life expectancy is increasing and so on. So how much is it increasing? What would we expect those born in 2030 to live to? Well, then we need to figure out what's going on from one end to the other. Let's see, I can get my line here. Something like what's happening on that line. That's where we're at. And happily enough, it did it in white, so we can't really see it. So let's figure out what we can do. I'll draw a black line in there. So we need to figure out how much it went up versus how far it went side to side. So let's figure out how much it went up. We'll take the 81.9, and obviously I'm looking at the females chart. And we'll subtract the 71.1. So that's how much the yellow bars went up from the left-hand side to the right. And we'll divide that by how much they changed side to side. So we'll take the 2020, which is the right hand, and subtract 1950, which is the left hand. So 81.9 minus 71.1 looks like, what do we have, 10.8? And 2020 minus 1950 is 70. So that's, looks like a nice division problem. Let's go ahead and clear my screen here, and I can actually speed this up by typing on my number pad. And I get 0.1542. So I'll write 0.154. What in the world does that represent? Well, let's talk about what that represents. The top numbers are age or years. Oh, years, living years. And the bottom is actual years. So we've got life expectancy over the number of years. So we're expecting to go up 0.154 years. And again, that's life years, age. Maybe we should do age. Per year. So every year after 2020 or in the middle, we should add 0.154 years to your life expectancy. So in 2021, we would take 81.9 and add 0.154 and get 82 years. So in 2030, which is 10 years later, we're going to add 1.54. In 2030, life expectancy is the 81.9 plus 0.154 per year times the 10 years. So if I take that calculator again, 81.9, oh, that's not a 81.9. I'm going to add to that 0.154 times 10. And I get 83.44. So that's the life expectancy of a female who was born in 2030. So that's another use for graphs. Graphs tell a lot of information at a glance, and later we'll talk about how you can lie with them. But for now, we're going to talk about how to read them and how to interpret the information, and then use that to maybe extrapolate into other areas. So it was just a matter of finding how much it rose over the amount of time, and then adding that to whatever the number of years is after that. We've got another kind of graph that we will use called a line graph. And these we see very often in the news. It's a common way to share information. This one is talking about cigarette use by US college students. Notice in 1982, which is on the left side of the graph, one of the things I often do when I see a chart is I try to understand what we're talking about. And so I look at the axes, specifically the labels. If you get a graph without a label, don't even trust it. You need labels, otherwise it's worthless. So on the bottom, we've got years. 1982, 1990, 98, 2006, 2014, etc. On the vertical axis, the vertical line on the left, we've got percent of college students. So how many college students, and based on the title, how many are using cigarettes? Notice from 82 to 90, it dropped from 24%. Over here, I look at that and it's right by the 24% down to here. Now to read how many percent that is, you just come right over here and it's not on any particular line, but it's somewhere between 20 and 24. And it's closer to 20. So I might say it's 21% in 1990. Now, for some reason, college students started using cigarettes again up to 1998. And then they've dropped since then. Now, one might ask themselves, why would it go up? What happened between 1990 and 1998 that would cause an increase in cigarette use among college students? And that would be up for debate, as are all why answers in the social sciences, but we can come up with lots of reasons. We could think what's happening in the world between 1990 and 1998. President Clinton was in office in those years. Did he have any effect? How would I know? Would it be the way society was behaving in general? Perhaps. Why would it drop? Did other things replace it? Was there a greater awareness placed upon the effects of cigarette use? I've noticed that it's become something of a social faux pas to smoke, whereas before it was much more common. And maybe that's all it is. Maybe it's peer pressure. But it's dropped down here to approximately 8% by 2020. So a definite change. Vaping wasn't around in 98 and it is now. Maybe that's part of why there's been a change. But they might ask, well, how many college students were smoking in 2006? So we come over here to 2006, go up until we hit our chart. There's the point, work our way to the left until we can read the value. And it's below 20, but above 16. So probably about 19% because it's really close to the 20. That's how we read those charts. When was it the most? You go to the highest point on the graph and drop straight down to figure out when that happened. That was 1998. What was going on then? There was a presidential election that year. That's when President George W. Bush was elected. He became president next January, actually. In 2001 was when the Twin Towers were hit with the planes. And notice things have dropped since then. Do those affect it? I don't know. But they're worth considering, I think. So one of the things we will do, and we kind of did it with the earlier one, was figure out a mathematical model that will highlight what is going on. And if I come back to this life expectancy graph, I can share with you that the book gives us a mathematical model for life expectancy, hence the E, of males. And there's life expectancy is 65.6. Notice that's where they started, plus 0.16x. And the 0.16 is really close to this 0.15 we got for the females. So the life expectancy of males is increasing 0.16 every year. So now what would it be life expectancy in 1965? Notice this life expectancy model, this is the mathematical model, starts in 1950. So in 1965, that's 15 years later. So the X will equal 15. Because this equation, this mathematical model started in 1950, and we are looking at a time 15 years later. So I can go to my equation and I can replace X with 15. And when I write it like that with parentheses, it means multiply. So let me go ahead and clear this out, and I can just take the 65.6, not 0.5, but 0.6. And I will add to that 0.16 times 15. Now, some of your calculators may not take that directly and work with it. Notice we got a 68, by the way. Does that fit with our graph? 65 was halfway between there, halfway between 66.6 and 67.1. Well, no, 68 isn't between those. But that's one thing about data, is that our mathematical model does not match every year. However, it matches most of them. And so it's just a general trend. And we came up with a value that doesn't quite work as well. But I was saying, with some of your calculators, you may want to do 65.6 plus and use some parentheses to force that multiplication to happen first before we add. And that's, we'll get into later. It's called the order of operations. But sometimes some of your calculators will need an extra set of parentheses to make it do what we need done. So that's how we'll use these mathematical models. Once we have those, we can plug in a value for X to determine what the corresponding value would be if the mathematical model matched our data perfectly. This one doesn't match it perfectly, but it's pretty close. And we proved that because we came up with 68, which is higher than the values on either side. Okay, so now we've covered rounding and we've covered how to look at various graphs to interpret those and get information from them. If you've got questions, let me know.